Hey friends, remember those amazing 3D models of cities and landscapes that you can find on Google Maps? Have you ever wondered how they do it, or have you ever wondered how you can make your own customized 3D maps? Well, look no further, because in today's tutorial I will show you exactly that. That's right, I will show you how you can create some fascinating 3D model city and landscape buildings in R. So the first thing we will do is I will show you where you can find free data for any place in the Netherlands. The second thing, I will show you how you can load this data, crop it, resample it, and make it work for you. And the third thing I will show you is how you can render this data in rayshader and turn your 2D images into a fascinating 3D city models. So let's get to it, but before we start, remember to hit that subscribe button. We'll start off our journey today by installing and then loading the packages that we need. So let's first of all define a list of libraries that we want to install and then load. The first one that we need is to work with raster files, and that is Terra. The second one is to work with polygons, so this is the asset package. And then the final one is for rendering the scene and also the object, which is rayshader. That's it, just 3 libraries. The second thing is to check if these libraries are installed. So first of all, we're going to go ahead and check in the row names. So in the row names of installed packages, whether these guys exist. So installed packages, just like this. Okay, and then if they don't exist, we need to install them. So we need to define here an if-else statement. So if any of the installed libraries equals false, then we open this curly brackets and then we say basically install libraries or install packages. But we don't install all the packages, we install only those packages among the libs that are not among the installed libraries. Okay, and then once we have installed all the packages, we then just need to load them. And loading in R is pretty easy. So we simply need to apply to that libs list a library function in R, which is used for loading packages into R. In today's tutorial, we'll be using 2 types of data. So the first one is the LiDAR data. LiDAR is simply a remote sensing method, which is used for measuring the height of objects by using a laser. So you take the laser and then you measure the time that it takes for this to reflect from the object back to the receiver. So that's one. The other one is simply orthographic photography of the terrain with true colors of the terrain. So those are the 2. And honestly speaking, it's very rare that countries open this data and then offer it. And it's even more rare that countries like the Netherlands in this case offers these files for free for the entire country for any location on a grid, which is simply amazing. So I'm here at geotiles.nl, which is an aggregate website taking from different Dutch sources these types of data, and then allowing us here to also download them. So without further ado, I just want to show you how this looks like. So you enter here at geotiles.nl, then you click here, and then you are able to choose one of the grids here with the appropriate data. So I want to go with The Hague, and I want to choose the center of The Hague, which is this 30 GZ1. So I'm just going to click on this, which is going to open a new window offering me different files in different resolutions. So what I'm interested here are these raster LiDAR files. This is what I'm interested in, and I'm interested in this DSM. As you can see, it's a very crisp resolution. So it's either 5 meter or half a meter. So in this tutorial, we'll be going with a half a meter, and then you have these different, let's say, generations of or versions of these raster files. With the latest one being this one, AHN4. So we're going to be going for AHN4, half a meter DSM, so this one. The other DTM will offer you LiDAR data, but only for natural objects. So for buildings, you're not going to be able to have it. And we want to have this in order to determine the elevation also of buildings. So we're going to go ahead and you can either download this file to your working directory, or what I'm going to do is simply copy the link to this file. And then we're going to be using R to download this file and then load it. So that's one file that we're going to be fetching here. The second one is the aerial photograph. For this one, I don't need to spend much words. So basically, it will offer you an image, or in this case, a TIFF file of the selected area with the true colors taken from the aerial photograph. And here, again, we have several options. So this is, again, a very rich one. The last one is from 2022. So this is the one that we're going to be fetching. And there are two options. So RGB, so these are the red, green, blue values. And this is the one that we'll be taking. So this one is 87.7 megabytes. So it's not that big. So we'll also copy the link to that file, but we will not be downloading it. We will be actually loading it directly using Terra into R itself. Those two links that we copied, I pasted them here into the editor. On line 34, you will see the link to the zipped LiDAR file. And on the line 35, you can see the link to the Orthophoto file. So we're going to start off by downloading, unzipping, and then loading into R this LiDAR file. So to do that, we need to wrap this link around it. So we need to wrap it with quotation marks, and then we need to create here LiDAR URL. And now that we're at it, we can also create the name of the file, which we're going to download. And to get this one, we can simply use base name LiDAR URL, which is going to get the name of the file together with the extension, which is zip in this case. And then we just need to use download file from base R. Over here, we need to pass the URL, which in our case, it's LiDAR URL. After that, we need to pass the destination file name. So this is going to be this LiDAR file that we just created. And then the third argument is the mode, which is the binary mode, and in R, it's denoted with WB. Once you download the zip file, we can easily unzip it using unzip function from base R and simply pass this LiDAR file name, which, as you remember, has this extension zip together with the name. Okay, once we unzipped, we can then load it into R. I'm going to create here something which is called LiDAR_rust to simply denote that we are here dealing with raster file. And to load raster files, we'll be using Terra rust function. Okay, so what you can do here, you can simply pass now the name of that file that we unzipped, or you can programmatically, as what I'm going to do here, I'm going to use this LiDAR file name. I'm going to then remove that .zip extension, and then I'm going to add to it .tiff extension. So here is how I'm going to do that. First of all, I'm going to use gsub here. Gsub is used for basically regex, so replacing expressions in R. And because we want to replace, or we want to get rid of everything after a dot, we need to use this simple expression here. So / and then dot and then asterisk here. So this is going to replace, or this is going to replace everything after the dot sign, and then replace to what? Basically empty sign, or we can also replace it to tiff. It doesn't really matter, but let's simply just do this. And then we're going to apply this to this LiDAR file. And then finally, what we can do here is simply use the paste function to glue everything together. So we're going to glue this one together, and we're going to also glue together with this new extension, which is .tiff file. Okay, so once we do that, it's fairly easy from here. We simply load this file, LiDAR rust, and then we can also inspect this rust file. Let's do that fairly quickly. So what we can do here, simply run this. And what we can see, yes, because we use Terra, this is a spat raster. It has a pretty high resolution though. So remember, we are dealing here with a very high resolution. So it's 12.5K by 10K. Resolution is 0.5 by 0.5. And then these are, of course, meters. So this suggests that this coordinates reference system is using meters. It is a bit strange, you haven't seen it, but it's for the Netherlands. And then here we have, of course, the source name and name of the layer. All right, our next step is to get also this data. And here we will be using Terra Rust to directly load into R without downloading to our hard drive. So this is what we're going to do. I'm just going to create a new object, which is going to be called ortho_rest. And then here I'm just going to use Terra Rust, and here just put quotation marks around this URL, which is going to directly load this into R. And then after it loads into R, we can also inspect this file as well. Also making sure that they also has same coordinate reference system, which is the case. It also has a pretty high resolution, so it's even a bigger resolution. So it's 25 by 25 meters, which we will need to account for, given that the other raster file has a lower resolution. And here it also tells us what is the extent. And also, very importantly, here we have actually colors as well. So we have true colors. So in case if you're wondering how this looks like, you can also use Terra to check that. So you can use Terra, and then here, because this raster file has RGB colors, you need to use plot RGB, and then you simply pass this ortho rast here. And once you run this, you should be able to see something like this. So the LiDAR and orthographic files are pretty large, and we don't need the entire area. So what we're gonna do is crop a certain area of our interest, and for that purpose I went to Google and I chose the coordinates for the Dutch Parliament, which actually falls within this area. So what we will do is we will use these coordinates. We're going to create a buffer of 500 meters around these points, and then we're going to crop both our raster files using. So let's get to it. The first thing is to actually define these coordinates as an asset object so that we can use them for creating a buffer and then cropping those raster files. I'm going to create an object called chords, and then here I'm going to define first of all these coordinates as a data frame. Okay, so the longitude here is the smaller value, so I'm just going to pass it here, and then the latitude denoted by lat here is this bigger value. So they need to be in the numeric formats, so that's why I'm not putting any strings around them. Then we're going to place this into a pipe, and we're going to call to rescue the asset package, and we're going to transform this into asset object. So for that purpose, we're going to be using st as sf, and because we are dealing here with points, we need to also define chords, and chords here are of course long and lat. It's very important that you do it in this order, by the way. So first longitude and then latitude. And the final thing is we need to tell asset package what is the coordinates reference system. In our case, st as CRS, and or actually only st CRS. So 4326, so WGS84, that's the one. And in the final step, what we want to do is we want to transform this into the coordinate reference system used by both raster files. And this is how we're going to do this. We're going to use actually Terra here, CRS function from Terra, and we're going to just pass this object, which is, for example, so either of them would suffice. So we can just use this ortho rest here. Okay. And yeah, once we do that, we can actually inspect this newly created object if it makes any sense for us. So I'm just gonna erase this and inspect this. So as you can see, we have a point coordinates here, so it's just one feature. It has the same coordinates reference system as the two raster objects, so that's successful. And here also shows us the coordinates once we transformed it into this new coordinates reference system. Okay, the second step is to create the buffer based on these points. So that's going to be pretty easy. I'm going to create something which is called Hague buffer. And here, instead of going for asset package, which we did in the past, we're going to use Terra to create a buffer. So I'm going to now introduce a new function to you. So it's simply Terra buffer. So over here, what we need to do is we need to coerce this newly created object chords into a Terra-friendly vector format. So that's why I'm using here Terra vect. And finally, we need to decide what is going to be the radius here. So if you are working with a lat-long coordinate reference system or other coordinates reference system that is a metric one, like this one, then simply here you can put how many meters you want. So we are here telling Terra that we want the buffer to be 500 meters in radius. Once we have the buffer, we can then crop both of the raster files. We're going to start off with LiDAR, and I'm going to create here LiDAR crop objects. For cropping, I'm going to be using crop function from Terra. Over here, we need to define 4 arguments. The first one is what we want to crop. So we want to crop this LiDAR rust. The second argument is what we're going to use to crop this one. So we're going to use the same buffer. The third argument is that we want to keep everything that is inside the buffer. So that's why we're saying here snap equals in. And the final one is we want to turn mask equals true, which means everything outside of that is going to be turned into NA values. Okay, and then once we have this, we can also plot so that you can see what we actually got. And once we plot this new LiDAR crop object, you should be able to see a cropped object and also with the round edges around it. So everything that we did here, we should also do with that orthorast file. So what I'm just going to do here is copy this, move a bit down, and then just replace here with this ortho. So I'm going to create ortho crop, and here we're going to be using ortho rast, and then finally here we will be plotting this ortho crop, so that once you actually run this whole thing and then you plot this newly created ortho crop object, you should be able again to see something like this. So you remember when I said that the LiDAR and the orthographic files have different resolutions? Well, we need to account for that fact because otherwise we won't be able to render it in rayshader. Luckily, Terra has a function which is called resample, which helps us readjust the resolution of one of the raster files using another raster file as a foundation. So because the orthographic file has a high resolution, we will readjust it, so we will downscale it to the resolution of the LiDAR file. So we're going to create a new ortho file here, which is going to be resampled. And then from Terra, as we said, we're going to use resample function. The first one is the object that you want to rescale or readjust. So in our case, that's ortho crop. The second one is what you're going to use as a basis. So it's going to be LiDAR crop. And then the final one is the method that you want to use. So here there are different methods. There is the one that is default is the bilinear model. So it's bilinear interpolation. And this is one that comes in handy in our case because both of our raster files have values that are not categorical, so they're continuous. There are also others like cubic spline, etc. So we're just going to be going for this bilinear because we want to use the orthographic file as a layer in rayshader, as we did as one of the previous tutorials. Here we need to save it as a PNG file. So here's how we do it. First of all, we can use Terra write raster. And then here we need to define the file that we want to turn into an image. So that's going to be the one that we already resampled, so ortho resampled. Here then we need the file name. So we can, for example, use Binnenhof, which is the name of that actually area that we used as the centroid. So that's going to be the name. And the final one is actually optional, whether you want to overwrite if you already saved something under the same name. Okay, and then once you save this, you can actually load it back, but this time as a PNG file. So we can just call it image here. And then we need also the PNG library and read PNG. And then here we can simply load this same file name. If you looked a bit closer at that LiDAR file that we cropped, you will notice there are a lot of white spots there. These are basically missing values. And if we actually go ahead and use this in rayshader, these are also going to be blank and they're not going to look good. Luckily for us, Terra has another solution. This time it offers us to impute values, missing values, based on different methods. And this function is called focal. So we're going to be using this one to impute values, to interpolate those values that are missing. We're going to be creating a new object called LiDAR crop, and then let's call it predict. Why not? So from Terra, once again, we'll be using focal. Now, within this one, the first thing is to specify for what we want to predict the missing value. So we're going to be using LiDAR crop. The second one is the weights matrix, which could be rows by columns or simply an odd number. So I'm just using here 9. The third argument is how you're going to do it. What is going to be the function? Well, I'm going to use the average values from surroundings, so neighboring ones. And then here, what I want to do is I want to do this only for the NA values. I don't want to replace other values that already have values. So here what I'm going to do is I'm going to say that NA policy equals only. So do this only for NA values. And finally, I'm also going to remove anything that is NA afterwards. Okay, so once we have this, we can then plot and then see the difference between the two ones. So we can also plot this one. So there is a slight change that you can notice if you plot this one and then the other one next to it. Some of those fields that are white, smaller ones, are now replaced with the new values, but you can still notice that there is this kind of a pond which still has the missing values. Well, now that we replaced most of these values, what actually remains are just these canals and ponds, and we can safely assume that these have negative values, so they are below the sea level. So what we can do, we can assign them the minimum value of our raster file. So something which is minus. So we can actually even see what are those values. So let's quickly inspect what are the values of this LiDAR crop. So it says here, exactly. So the minimum value is minus 3.4 and the maximum value is 85. So we can go for this minus 3 and use this one as the base value for those that are not still replaced. But how do we replace? So Terra has something which is called if-else, and we can use that. Basically, it's an if-else statement, which is going to help us determine what we're gonna change here. Okay, so what basically we're going to do is we're going to use this one, LiDAR crop predict, and we're not going to be creating a new object, which is basically we're just going to call this one. Okay, so here we're saying if this is NA. So in cases where we still have NA. The second step is what do we turn this into? Well, let's turn it into the minimum value, which is minus 3.4064. And then the final one, if this condition is not met or if it has the value already, we simply just give it the value that it already has. And then our next step is to finally render the scene. But before we do that, we need to turn this LiDAR crop predict object into a matrix because a rayshader works with matrices. So we're going to be using here rayshader, a raster to matrix function to do that. So LiDAR crop predict. Okay, and once we have that, we can just put this newly created LiDAR mat into a pipe. And then first thing is we're going to define here rayshader height shade. So basically we'll be using the LiDAR one for our height shade, so that's very important. The second one, we'll be adding that overlay. So add overlay. So here we'll be using this IMG that we loaded. The second one is the alpha layer opacity. So how transparent is going to be. And here one means that the basically this overlay is going to be completely visible while everything underneath it is not going to be visible. So here we are doing this because we only want this LiDAR one to be used as a height shade, and we want the overlay, which is the orthographic image, to be completely visible so that we have a crisp view of all the buildings, streets, trees, and everything else. Okay, and then once we have this, we simply need to plot. So we can use, again, rayshader and then plot 3D. And within the plot 3D, again, we need to define that we'll be using this LiDAR mat. Then the second thing, there are other things. So I would not like to have any kind of a border around the seed itself. So that's why I'm gonna turn it off using this solid equals false. And then for the heights, I'm going to be using the Z scale, which is 1. So that means that sparks are going to be very high. If you want to tone this down, you can increase the value of Z scale. Okay, then we can also choose the zoom here. So for the zoom, I'm going to zoom in a bit, which is 0.6. So the range is from 0, which is completely zooming in, to 1, which is completely zooming out. So I'm somewhere in between. Then I'm going to choose the angle of the scene to be 45 degrees. I do also want to tilt it using theta, and I'm going to tilt it 30 degrees in the counterclockwise direction. And finally, the window size here, I'm just going to go for the window size, which is 800 pixels. And then if everything goes well, once you run this, you should be able to see a scene that looks something like this. If we're happy with the scene, we can go to the final stage, which is rendering the 3D object in high quality using rayshader, render high quality. So within this one, there are several things that we should define. So the first one is the file name. So here, what you need to do is simply define here as a string, then choose your extension. I'm going to be saving this as a PNG file. And let's say I'm going to just use here 3D city building, something like that. Okay, then the next one is going to be whether I want to have the preview of the rendering object. I said yes. The third one is I'm going to turn off the lights. That's because I'm going to have a customized lights using an HDR file, which was predefined. We also did in the previous tutorial where we were also using some of the predefined lights. In this tutorial, I'm going to be using the very same light. So if you're not sure how we downloaded this file, how we got it, you can check out that previous tutorial. But what is really important to know here, we will be defining here environments lights and here passing the object. Now what is very important here is that you pass the pathway to this file. So if this file is in your working directory, that's fine. If it's not, you need to pass here the full so that rayshader knows where to look for this HDR file. Okay, and then we can also then customize several things about this environment light that we'll be using. The first one is the intensity ENV. So this is how intense it's going to be. I'm going to go for 1 here. If you want this scene even lighter, you can go for an even higher value of this, but be careful because it might become too white. And then the final one is what is the angle that you want to have. If you are fine with the current angle of the lights for the specific Air Museum playground, then you can just omit this one. But I do want to rotate it by 90 degrees because I want the light to come from something like southwest and the shadows ending somewhere in northeast. There are some other here attributes that you can also define. One of them is whether you want everything to be run parallel. So here is where you can utilize if you have multi-cores in your processor. One of the things that I like to turn off when I'm working with rayshader is this interactive option, which allows you to actually move the scene and do God knows what, but that can actually end up in crashing your current scene. So I just tend to kind of turn it off. And then the final one is defining the width and the heights in pixels. So I'm going to go here for a very high, well, not very high, but high resolution, which is 4000 by 4000. And that's how you do it. If you're wondering whether there are files for other countries or cities, I'm going to drop a link to some of them in the description box below, so do check them out. If you are interested in replicating today's analysis, I've also prepared a link to the GitHub repo in the description below, so also do check that out. Feel free to clone it, modify it, reuse it as you see fit. Also, if you are new to R and you seek to expand your GIS and data visualization knowledge with R, I've prepared a few cool tutorials for you, so do check them out. And also, if you have any questions, feedback, or comments, you can reach out to me here on YouTube, but also on Instagram and X. See you next time.